Okay, cool. Social graph is a very important workload, especially for companies like Meta, like Snap, and so on. So today we have Dr. Aaron Campbell, from Meta, and Audrey Chen from UC Berkeley, and Yang Zhang from PingCAP. So Aaron will first describe the evolution of TAO, a social graph data store at Meta. And Audrey will give an overview of TAOBench, a benchmark for large-scale social networks. And finally, Yang will explain the reason behind TiDB's performance in TAOBench among several other distributed SQL products. Okay, so let's start with Aaron. So Dr. Aaron is a research scientist in the system and info organization at Meta. So as we know, Meta is one of the largest social network companies in the world. So prior to joining Meta, he received his PhD from Harvard University. Let's welcome Aaron.
Great. Thank you so much for the introduction. Cool. Slides are shared correctly? Yeah, awesome. Cool. Awesome. Yeah, great. Just double checking. Cool. Thank you so much for the introduction. As mentioned, so I'm going to be talking a little bit about TAO, which is the data store that we use for our social graph here at Meta. And this will lead a little bit into Audrey's talk later. So as a second talk today, Audrey will be talking about our recently released workload TAOBench, which kind of talks about all of the different ways that, basically all of the different inputs to the social graph. But to get kind of an intro, and especially since we're going to be talking at some length about transaction processing and the social graph in the second talk, this talk will be talking a little bit about how TAO has evolved, especially with regards to consistency guarantees, in order to be able to serve those kinds of transactional and non-transactional workloads. So first, I'll dive in by introducing everyone to kind of what is TAO, what is the social graph, giving some examples of data that might live on the social graph. I'll dive a little bit into the consistency failure modes that we can see in the social graph and how they can break products. And then I'll walk through our scalable consistency solutions and how we're able to provide both read and write consistency at metascale. So to start, let's talk about what the social graph looks like, what the data model is, and what kind of things we might store. So kind of a classic social network product might be that, say, we have Alice. Alice is at the Golden Gate Bridge. She checks in there with someone named Bob. Kathy comments on it, wish you were here, and David likes that post. So that is stored as a series of nodes and edges on a graph. So each of the kind of individual players in this, so Alice, Bob, David, Kathy, the location, Golden Gate Bridge, the comment, each of these are stored as graph nodes, or what we call FB objects. So each of these have some identifying ID number, some type, whether they're a user or a location or a comment, and whatever data might be associated with this. We then connect these different nodes with graph edges that we call associations, or SOAKs. And these might have some type or some data, but in general, we'll say, okay, what is the relationship between these two graph nodes? For example, we have some comment. It might be liked by someone, so that's an association. It might be authored by some other user, that's an association. The users themselves may have friend relationships. Those are all encoded as associations. And this allows us to build up some kind of very, very large graph that we use to power Facebook and other products. It turns out the API for this is actually very different than what you'll see for a SQL API, and it's intentionally kept very, very simple to make things easier for product developers. So from the read side, we only support a limited number of operations. We support point reads on nodes. We support point reads on edges. And then some kind of basic range and count things. Let's say, okay, hey, I have some person. How many friends do they have? So that would be encoded as a range operation. And on the right side, things are, again, kept simple. So we support point objects, so create updates and deletes for graph nodes, adds and deletes for edges. And then we have what we call multi-writes, which allows us to compose any number of point operations into something that we know that we want to be atomic. So this allows us to kind of provide some input API for consistency to our social graph mutations. So how do we actually kind of power the data store that stores all of this graph data? So this was really described in a 2013 paper by Nathan Bronson. So I'll give that kind of basic outline to start. So we have multiple regions all over the globe. We have a browser that wants to then now send some sort of mutation into one region. So what it does is it first hits a web server. The web server has a cache sitting behind it that we call the L1 cache. In this initial description, there's one L1 cache for every web server. If it wants to do the write, it then goes through the write-through cache, both through the L1 cache, through the L2 cache, figures out which region is the primary for the data it's trying to write. We'll send the data to that region, and then we'll persist it to DB. And as you'd expect for kind of something that's across regions, our data is all sharded. This allows us to then scale horizontally as well. So there's a few key features of TAO. One is it's really focused on scale. So TAO serves 1 quadrillion queries every day for Meta's billions of active users. It's a strongly read-dominant workload. So we have 10 billion read QPS and 10 million read QPS served by our data store. And especially initially, in order to really prioritize availability for the social graph, there were very weak consistency guarantees. So TAO by default is only eventually consistent in order to kind of be scale first and consistency second. But it turns out that as Meta has evolved, that really hasn't been sufficient for all of the products that we're trying to build on the social graph. So to kind of give a basic example, let's take a subset of this. Kathy wants to write a comment on this check-in and see in what ways consistency breakages can cause problems. So the first is, what if we have a write parcel failure? So when there's a successful write, Kathy creates a comment, and we can connect an edge between that comment and the user to say who authored it. But we can imagine that say, hey, because we don't have built-in atomicity on these writes, we could have the FB object write fail. So you might just see, hey, Kathy authored something, and you go to see what she authored, and it's missing from the database. Or similar, you can have a case where the edge write fails. So hey, you have the comment, but you can't actually see what's authored by because that information wasn't persisted to the database properly. But even if the write succeeds, you may still read back different information than you expect. So the most simple failure here is what we call read your writes failures. If Kathy creates a comment, she should expect to be able to see that comment immediately. But you can imagine a case where, especially if like the users and comments are on different shards, she may only see the edge and she might be missing the comment, or vice versa. And the sort of even more complicated case is where you end up with torn reads. So Kathy creates the comment. You would hope to be able to see that comment, globally. If David now opens his phone and wants to see that comment, he'd be able to see it. But you may end up with the same breakage where, the comment's missing and the edge is there, or vice versa. So now I'm going to talk about how we address each of these 3 failure modes in order to be able to make these mutations a lot more intuitive for developers and be able to provide a better product experience. So let's start first with the write parcel failures. This has kind of a well-known solution in the single shard case, which is we basically use MySQL, in particular MyRocks built on top of RocksDB. And I will kind of defer this to saying that we assume MySQL transactions work. How exactly they work and how to do that efficiently can be a separate talk that I'll defer for now. But the idea here is the product will send in what we call a multi-write that will encapsulate all of the writes and say, hey, I want atomicity for this set of writes. We can send it with a MySQL transaction, wrap everything inside the kind of standard transactional code, and know that this will be executed atomically. However, really relying on only single shard transactions leads to a lot of complications for product developers. First, it really requires them to think ahead. So it requires explicit co-location from developers during the feature implementation. If you have a bunch of stuff that you want to be atomic, you need to know ahead of time that it should all be co-located. As everyone knows, products tend to develop pretty organically. You get new user requests, you have new things you want to build. And then this can require expensive migration to be able to move everything around if for an already existing product in order to be able to provide these sort of guarantees. Co-location is often impossible with shared types. For example, like the kind of user object is used by a lot of different products. You can't necessarily satisfy every co-location that every single person wants with a user and still have a graph that works. So that leads to a lot of kind of problems with these commonly used types. And overriding the default sharding can cause significant imbalances. If you have some major celebrity, you put everything for that celebrity on the same shard, and then they like release a new album or release something new that causes a lot of traffic. You suddenly get a shard that has, potentially millions of queries to it in a second, and that can really cause problems for the underlying system. The takeaway from this is that cross-shard transactions are really necessary for scalability and developer experience. In order to be able to do this, we use a kind of a standard 2PC system with persisted progress. So multi-write comes into some region. It reserves, in this case, we'll assume that A is being written to region 1 and B is being written to region 2. So we reserve A on region 1. We forward kind of the rest of the requests to whatever region they're supposed to be in. We're able to reserve that on 2. We say, report back to region 1, we had a success. And then based on whether we have success or a failure, region 1 will decide whether we want to do a commit or a rollback here. So, in the commit case, we're able to resist the write. And in the rollback case, we're able to undo the write to get back to the initial step. What can cause problems, though, are what happens if one of these writes get lost, or there's some failure in the middle that doesn't kind of work nicely. Let's say a region is network partitioned, or a region goes down entirely. How can we kind of handle these sorts of failures and still ensure atomicity? So in order to do that, what we do is we basically persist progress. So when we do the reserve, we write some data into our system to provide metadata saying, okay, we started a transaction, we did a reserve, and we have a system that will then tail this metadata and ensure that it reaches a conclusion within a reasonable period of time. So we call this the transaction coordinator. For example, in this case, we reserve A. The coordinator knows, hey, this is a transaction, we should also be able to reserve B. If the system goes down, it's able to basically go in, check the metadata, see where the transaction got stuck, and is able to then read the data, see where we are, and provide whatever sort of finishing things you need to have in order to be able to turn the data to a consistent state. For example, in this case, region 1 died still during the reserve phase before it could decide whether to go to commit a rollback. The coordinator can come in and say, hey, this got stuck, let's roll back everything in order to be able to ensure that TBC always finishes correctly, even in the presence of failure. What's also nice about this is it actually allows us to provide a bunch of kind of nice intuitive guarantees for mutations on the social graph. For example, we have this case where we have Kathy writing a comment. And I've said before, like, hey, you might have an edge that kind of gets lost. You might have some things that are weird. And that's actually really hard to program for. Because if I kind of write an edge, I always expect that both sides of the edge, for example, are going to be completed. So in that case, there's sort of this intuitive expectation that you have failure atomicity on a single element rather than kind of having only half an edge written. So what we can do is basically program in that we wrap all of these implicit patterns inside transactions. So this really lessens the burden on developers to have to think about, hey, what happens with each of these individual failures? For a bunch of these common write modes, we just say, hey, these are all going to be done transactionally automatically. And then they can think about kind of the more important parts of their product and not about, hey, what happens in each of these individual breakage cases. So that's how we handle write failures. But let's think a little bit about read your write failures. So at the beginning, and this will be talking a little bit more about how TAO has evolved, but at the beginning, this was provided rather naively. So what we say is, hey, if we have a user, we're going to basically stick a user to an individual web server. So whenever they do a write, it'll go through that web server. That web server will definitely have the most recent version since we know that they're always hitting the same one. And that's kind of totally fine. That kind of naively allows us to say, hey, we know the cache will be updated because we're always going through the same cache. We know that they'll always be able to read their own writes for that reason. As you may expect, though, this isn't really scalable. For example, what happens if that web server goes down? It turns out that having one L1 cache for every web server is really expensive. The L1 caches usually aren't doing that much. So it's a lot more efficient if we instead decouple the web servers from the L1 caches and really can optimize the number of each of those servers that we have independently based on their workloads. What happens in the case where you end up with having sort of failover, like if a region goes down, then how are you supposed to be able to handle read your writes? The web servers aren't available anymore. We have a global index with asynchronous replication from other regions. How do you want to handle this? All of these different scalability concerns meant that we couldn't really stick with this one user per web server case. Especially because it was hard across to, okay, well, now users accessing it from their phone and from the browser and from another browser and maybe over VPN. So it's much better instead if we try to just make things region sticky. So, hey, user will always try to access something from the same region, but we no longer need to lock into the same web server. And this allows us to do a few things. In particular, using something we called flight tracker. So the idea here is, hey, the issue that comes about with read your writes consistency is when you do a write and you read back, you basically have a missing write that you're not expecting. So what we want to do is we want to try to identify those missing writes, encapsulate those writes within what we call a ticket, and then make sure those tickets are available to every different path that the person may read from in order to be able to see this missing write. So how do we do that? We add a new flight tracker module within each region. So when you do a write, basically the web server sends the write to L1 cache, which will go through the database. And then on the return path to the web server in which it reports a success, it also returns a ticket, which contains all of the metadata from that write. The web server, invisibly to the developer, will automatically forward that ticket to the flight tracker service. What then happens on the other side is, let's say, hey, I'm now issuing a write to a different web server. that web server will grab the ticket from flight tracker containing all the metadata from that write, and will then forward it along through the caches to the global index. And that basically says, hey, I have a ticket that contains that write I was missing. Let's now apply that write invisibly again to the user in order to be able to kind of update the write to the most recent version that I should have seen, given that I'm expecting this kind of read your write behavior. So again, this applies both to the writes as well as to the global indexing services that we use. And you might say, hey, this is kind of expensive. I'm doing a quadrillion queries a day. Does that mean I have to do a quadrillion fetches for flight tracker? One thing that actually kind of happens here is when you do a single web request, it usually causes kind of a cascade of writes to the system. So what we're able to do is kind of fetch a single ticket and apply that to a whole mass of different reads and writes that actually happen on the web server. So we're really able to amortize the single ticket fetch over a very large number of writes, so it becomes a lot less expensive than it might seem at first sight. And this works really, really well in practice. So this is deployed in production for us now. We see that the service has 6 nines of availability, leads to less than 2% CPU RAM overhead in this product, and is able to successfully serve the sort of quadrillion queries per day. But what if you want something more general? So not just the single read your writes kind of guarantees, but you also want torn read guarantees. So not only can Kathy see the update that Kathy has made, but some other user, David, is also able to see the update that Kathy has made. So there's been some work on this by Peter Bayless in order to provide kind of read atomicity with what we call the RAM transaction. And just to clarify, so Audrey, who we're presenting later, was actually the one who did this work with us. So the idea here is that you have some user, Kathy again. She's going to want to read A and B, which are going to be stored on 2 separate shards. And in particular, shard A has some later version A2 than shard B does, which only has some earlier version A1. So what we do is we return both the value as well as some transactional metadata. So A2 knows it was written with some value B2, B1 knows it was written with some value B1. And when we're able to kind of collate all this data, we can say, hey, we know we're missing B2. Let us issue another read specifically to the correct shard in order to be able to fetch this missing value and make sure that we kind of satisfy the read atomicity conditions that we want. So we do that, we can fill in the gap that we need. However, there's a few reasons that this actually becomes really tricky. So one of them is performance. Note that, as you'll see in Audrey's presentation, most of our writes are actually done non-transactionally. So in order to be able to provide kind of support for read transactions, we need to make sure there's no regression for our non-transactional writes. We need to make sure that it's cache friendly and can handle hotspots as well in order to be able to serve these workloads at scale. This, as presented, has a lot of metadata overhead. You're now replicating all of this extra metadata all over the place. This can cause significant storage and latency penalties. And one thing that's kind of subtle is TAO actually doesn't have multi-versioning support. So you can imagine in this case, let's say B2 is overridden by B3 before you're able to do the read. If you now go to read B2, you see there's B3 instead, you have no way of recovering that old value. So what Audrey realized is that there's actually, what you can actually do here is you can actually cache the metadata for transactional writes in the recent past within the TAO cache itself to allow you to be able to serve these types of workloads. So the idea here is that the sort of, the transaction plus whatever data was stored will be stored in the TAO cache. So if we now issue the same read, we have the same thing where we come back with some sort of weird broken state. And if we now have, some transaction that comes in with A2, B2, and then some unrelated transaction with B3 that overwrites B2, what we do is we provide temporary storage within the cache that provides each version of B1, B2, B3. So we're basically moving this multi-versioning to the cache, and that's only held for a few minutes so that we minimize the kind of storage overhead that we might have. And the transaction information is also stored temporarily within the cache so that it's accessible, again, without many of these overheads. So now when we go to read B2, even though it's been overridden on the database, it's now still accessible in the cache, and we're able to kind of fill in the gap like we want to with the original RAM transactional protocol. And the important thing to note here is, again, we have a fairly small transactional workload. Most reads are still being served kind of in the fast path through cache, which makes this still able to be scaled at kind of and work at metascale. So just, again, to provide some summary of this, Audrey was able to observe less than 10% P99 latency increase for the system. found that 99.9% of reads are only requiring this one round, which really helps to prevent kind of the large-scale regressions that we might have for other heavier consistency systems, and less than 0.5% memory overhead. Great. So yeah, so thanks for listening to this talk. In conclusion, the idea here is TAO really provides a scalable data store for metasocial graph that allows us to serve our demanding workloads here. And even though it was initially built with weak consistency guarantees and eventual consistency, we've been able to layer on cross-shard transactions, flight tracker, and ramp TAO in order to be able to provide the improved consistency guarantees that are needed to make products intuitive for developers to write, as well as provide additional safety when it's needed. And the key for each of these strategies is that they're really bolt on. So none of them really affect non-transactional writes, which still provide the bulk of our workload, which allows us to maintain the overall reliability and efficiency of the system and only pay for these initial guarantees when they're really needed. So we'll know this was really like a mile-high overview of these different systems. I encourage you to check out Nathan Bronson's original TAO paper, Xiaoxi's paper on flight tracker from OSDI a few years ago, and Audrey's paper on ramp TAO from last year to be able to get the full details of each of these different protocols. Great,
okay, cool. Yep. Thanks, Aaron. Okay, so thank you very much for Aaron's talk. There are 2 questions online. So I'll just read these out. The first one is how to address the concern of single point failure of the global index. This is the first one.
So the global index itself is distributed. So there's a bunch of kind of failover built in there. I mean, if you have something that hasn't yet been replicated and a region goes down, then you're likely to have index failures. There are a bunch of other ways you can kind of improve that. But in the world in which you have a regional failure, then occasionally things have to fall back to kind of best effort guarantees.
Okay, cool, thanks. And the second question would be, sorry. Okay, yeah, okay, cool. The second question would be, is there any mechanism for concurrency control? For example, determining transaction sequence globally? Is there such mechanism?
Nope. So all of our transactions are done at the like individual shard level. And that's just again, that in order to be able to do something like global transaction, I think you need to like kind of build like that is something in which you're kind of starting with you want strong consistency. For us, because we're really trying to have this bolt-on approach where we don't have to pay for things otherwise, that's really led us towards this kind of shard-based model instead.
Okay, cool. Thank you. So is there any question on site? Is there any questions on site?
I have one question. Yeah, sure. I think it's impressive to see that you have like implement like additional like or stronger consistency without like much impact on the online workload and didn't increase a lot of like CPU cycles or memory footprint. I'm curious to see that what motivates you to do those like stuff, because I think what are the business like impact of those things? Could you briefly talk about that? Is this like, do you see like less outages or less on-call issues, or do you see like faster iteration speed based on those like new features you added on top?
Yeah, so I think it's some mixture. So the impact ends up being very product specific. So there's a few things. One has been the evolution of the products that have been on the social graph. So there's other data stores available. By adding more of these consistency guarantees, we can migrate more of them to TAO, where they can take advantage of some of the other kind of scalable pieces that we built into TAO rather than relying on the other data stores. And part of it is also that a lot of things want to run on TAO, but had like 1 or 2 kind of pain points where they had to do some sort of asynchronous fixes in order to be able to handle these consistency issues. By to adding these transactional semantics to be able to do basically synchronous atomicity guarantees, rather than kind of building, in many cases, they basically build their own transactional semantics on top of it for the like 1 or 2 points that they needed the strong consistency guarantees in the critical path. This allows us to simplify their workload because they aren't running their own fixers and really make things simpler for them so that they can concentrate on making the product better and not have to worry about all of the back-end challenges.
Okay, cool. Maybe a follow-up question is if you want to add some new features or new maybe stronger consistent guarantees on call, what are some of maybe top 3 or top 5 things you want to improve on top?
Yeah.
From the if we want to forward looking and see based on where we are today, what are the, let's say if we want to, what do you want to be in a year or in 2 years?
Yeah, I think there's kind of 2 directions for that. So one is usability. So there have been some talks on the Ent framework, which is the way that most users actually interact with TAO. There's kind of another layer of indirection that applies a bunch of additional guarantees on top. So really making, so we kind of added these transactional features recently, but making them a lot more intuitive for people to use is really a priority, especially because consistency is hard. One of the reasons that, I have a job and we have teams that are dedicated to this is that maintaining consistency guarantees in distributed systems and having product developers, especially in a way that product developers don't need to spend a lot of brainpower working on them, is really challenging. So I think kind of making this more intuitive, adding more kind of implicit consistency guarantees, and simplifying the interface to the point where users are able to say, hey, I think this is important. I probably want consistency here, or something very simple like that, and having us kind of take care of the rest of that, rather than much more specific, like, hey, I think these, please make these 5 things atomic and these 5 things atomic, is kind of the long-term goal. And then continuing to kind of increase the richness of the transactions that we currently allow.
Yeah. So maybe one final question, really quick question, is that what are the run short for? Is that I heard the word RAMP. What did that stand for?
Oh, read atomic. Audrey, you probably remember.
Yeah, read atomic multi-partition.
Okay, cool.
Thank you.
Yeah, link to the page.
Okay.
Okay. There's another question online. So, does TAO rely on any MySQL transition?
Maybe transactions.
Transactions? Yeah. So, I've talked it away here, but yeah. So TAO does, for the single shard case, rely on MySQL transactions in order to work. So TAO sits on top of MyRocks, which sits on top of RocksDB. Meta has our own kind of MySQL implementation. So yeah, so the entire thing assumes that MySQL transactions work well. Otherwise, handling things on the single shard level is really, really challenging.
Yep. Okay, cool. Thanks, Aaron. Okay.
Great, thanks so much.
Yep. Okay. So let's now move on. Okay. So give me a minute. Cool. So now Audrey will give an overview about TAOBench, a benchmark for large-scale social networks. Her work, TAOBench, was published in VLDB 2022. And Audrey now is a 3rd-year PhD student at UC Berkeley's Sky Computing Lab. Let's welcome Audrey.
Thank you for the intro. Cool. Yeah. So I will be talking about TAOBench, which is a new open source benchmark based on Meta's social graph workloads. So I'll give a quick overview of what we'll cover in this talk. First, I will discuss why we need yet another database benchmark, specifically unique patterns and characteristics that we identify in Meta's social graph workload make them interesting and important to capture in a benchmark. Then I'll cover what we're actually open sourcing, which involves both Meta's social graph workload profiles as well as a benchmark tool that can be used against both industrial databases as well as research prototypes. And finally, I'll talk about both the internal and external impact of our benchmarks as well. So to start off, social networks have been around for quite a while now, and they're still very, very popular, and they're supported underneath the hood by large-scale geo-distributed data stores. And as such, timely and online access to these systems is really important for user experiences. And some examples of these systems include Meta's TAO, as well as TikTok's MySQL. And the social network workload is especially challenging to support because of its extreme skew, high correlation, and read dominance. So while there are a lot of social networks, there are actually very few benchmarks in this area to guide research on the underlying data infrastructure. So the few benchmarks that we do have significant limitations. So 2 prominent ones that I'll talk about are LinkBench and LDBC. So LinkBench was built by Meta for analyzing and optimizing a single MySQL instance. So it did not contain any post-cache requests, though it was based on a production workload. And it also didn't capture any graph level transactions, which, as Aaron described, are very important part of the workload. And finally, it also didn't contain any sharding information, which can be important because sharding here is not just an implementation detail, but it can reflect user intent, privacy constraints, and/or regulatory compliance. LDBC is another prominent benchmark in this area, and this is more focused on graph databases. So as such, most of the requests are complex processing-intensive queries rather than serving queries, and it contains 29 different query types representing common social network actions, such as finding the friends of your friends, and it doesn't contain any sharding information as well. So lack of publicly available realistic workloads has been a detriment to both academics and industry practitioners. In academia, the scarcity makes it really difficult to probe and understand the limits of existing systems and how we can overcome them. And in industry, it becomes very challenging to evaluate new features and resolve issues without a reliable way to reproduce these request patterns. So what are we to do? Well, to address this issue, we've created a new benchmark, TAOBench, that accurately captures Meta's production workload. And to the best of our knowledge, TAOBench is the first open source benchmark that generates end-to-end transactional request patterns derived from a large-scale social network. So I'll first talk about Meta's social workload that we capture, focusing in particular on several unique patterns and characteristics that we believe are interesting and important for performance. So specifically, we profile the TAO stack at Meta. Aaron already went into detail on this, so I'll give a very brief overview. The key things to know that are relevant to benchmark and the workload is first that operates at huge scale. We have over 10 billion requests per second, and it's serving a wide variety of products. The well-known like Meta's family of applications, including Instagram, WhatsApp, are all served by TAO underneath the hood. And finally, it has a simple graph API with flexible consistency semantics. So as Aaron covered, while the system started out as eventually consistent, it now supports read-your-write consistency as well as transactions. And the RAMTAO paper describes the transactional part of the system. So in terms of the workload, we collected production traces over 3 days, and our paper has more details on how we made sure we captured a representative workload. But at a high level, we saw that this workload consisted mostly of reads, some writes, and very few write transactions. And as a part of this, we found many interesting features. The paper has details on all of these. Today, I'll cover 3. The first, about how read and write hotspots tend to occur on different keys. The second feature is about how transaction hotkeys tend to be co-located. And finally, how contention can often be intentional on this workload. And these features emerge from diverse applications running on a large partitioned social graph at scale, and they have significant performance implications, which are why they're important to capture in a benchmark. So the first feature I'll talk about is the read and write hotspots. So this graph here is showing the reads per day and writes per day for the like assault. So this is basically when you like something on Facebook, this creates an edge between you and the post or something that you liked. And we're looking at the top 400,000 write keys because the tail we find doesn't differ significantly past this point. So we're showing the reads on the x-axis and the writes on the y-axis. And you'll notice that there is one cluster on the left, and these keys are written to infrequently, frequently, but read infrequently. And an example of why this would occur is this could be someone like me who's not very popular on social media. I post something, but there's a lot of asynchronous jobs running in the background, where there's some migration tasks that lead to a lot of writes. On the other hand, the right side, you see that there are some keys that are read frequently and also written to frequently. An example of this, like Lady Gaga maybe post something. So a lot of people are viewing her post and also liking it, leading to this pattern we see here. So in conclusion, we see that read and write hotspots can occur on different keys, even for the same key type. And this is something that's not always covered in existing benchmarks. The second feature we'll look at is hotkey collocation. Specifically, we find that write transaction hotkeys tend to be collocated on the same few shards. So to see this, we'll look at the shard distribution of the top 400,000 keys for the three main product groups on TAO. And product groups basically represent families of applications that share data in the same product infrastructure. And you'll see the shards on the x-axis and the number of hotkeys on each of these shards on the y-axis. So for example, this pink circle is highlighting around 50 shards that have about 1,000 hotkeys each. And you'll see with this distribution that there tend to be a lot of these hotkeys are co-located on the same couple of shards. And upon further investigation, we found that these hotkeys were actually rarely part of the same write transactions. So standard practice would be you could do better load balancing by spreading these keys out in a more even manner on shards. But we found that a lot of these keys were actually explicitly co-located on these shards by application developers, because when they needed to send reads to the database, they could batch these reads and get a lot better performance. So we find that there's a trade-off between load balancing and batching of requests.
Yeah, that's interesting. Just want to make sure my understanding is correct.
Yeah.
How can we infer that the two keys are on the same shard from the graph?
Yeah, so we're showing basically for each shard. So you can think of each of the points here as one particular shard and the number of hotkeys on that shard. It's on the way.
So, but because they belong to the same product group, it's likely they are, I think, collocated.
Yeah, we're just
within the same transaction.
Yeah, so we're splitting them by product group because product groups tend to share the same data.
I see.
So it makes sense to sort of look at them within product group. Yeah, and you'll notice that these distributions aren't as simple as like uniform or Zipfian. So it's important we sort of capture these in a benchmark. On the third feature I'll talk about is the distribution of contention in the transactional workloads on TAO. So this is a CCDF, which is basically an inverse CDF, showing the breakdown of conflicts per day of key type. And key type, you can think of this as a proxy for application use case. So you'll see that at the top here, there are a lot of different use cases that have very few conflicts, and these make up the majority of the workload. However, there's a very long tail. So there are some rare use cases that cause a lot of conflicts. And digging deeper into this, we found that actually the vast majority of write-write conflicts were due to intentionally racing writes. So an example of this is, let's say you have an application and it has live video time slices and it wants to annotate them. So it needs to basically create edges in the social graph to link to the live video time slices. And to ensure timely processing, it'll basically send multiple create requests that are redundant and relies on the system and the transactional guarantees that the system provides to ensure that only one of these requests will succeed. And the application can safely ignore any conflicts it sees. And we see that these conflicts are intentional and they're important to capture in a benchmark so that we can replicate and study this feature. So given the lack of existing benchmarks that capture the interesting features we observed at Meta, we decided to open source a new benchmark, TAOBench, that accurately replicates these request patterns. So through TAOBench, we first open sourced Meta's production workload. Specifically, we have 3 workload configurations, including the overall TAO workload that capture different aspects of these request patterns. And in addition, we also open source a flexible framework for benchmarking social networks with many database adapter layers that are already available. And it's also very easily extensible to other systems. And we've seen real impact at both Meta and beyond, which we'll talk about a little bit later in the talk. So in terms of designing our benchmark, we first parameterize the workload, the small set of parameters that we show are sufficient to replicate production workloads. They are the following, and they can be split into 2 categories. So the first are ones that are very general and directly applicable to other data stores. These include transaction size, sharding, operation types, like read or write, and then request size, the actual data sizes of the items. The second category are ones that are more unique to TAO, but these properties are captured on other systems, so they're pretty easy to translate to other systems. So these include a sock type, which are basically correctness constraints, preconditions or integrity constraints, and also the specific read tier. So which tier, either the cache or the database the request is coming from. With these parameters, we built our benchmark, which consists of scalable distributed drivers that run the workload, and we have a very simple API that's based on TAO, which Aaron covered earlier. It's very similar to key value store, and as such, it's very easy to map to other systems, and we currently support Cloud Spanner, CloudDB, MySQL, PlanetScale, Postgres, TiDB, and Ubuntu. So to validate that our benchmark workloads are actually representative of those in production, we basically evaluated our generated workloads against their production counterparts. Since a lot of the features we already matched by construction, such as like transaction size or the operation type distribution, we decided to focus on two key features that arise from interaction between the system and the workload. So these are the latency distribution and contention errors. So this graph I'm showing here, so for a transactional workload T1, we're looking at the latency breakdown of the production workload as well as our benchmark workload, and we find that these are not statistically different. And furthermore, we're able to replicate the latency tail, which has significant implications for performance. Cool. So now we'll describe both the internal and external use cases of TAO, which has been able to support a wide range of testing that was not previously possible, as well as identify performance bugs and opportunities. So at Meta, it's been used for a large range of use cases, including testing new system features and optimizations, as well as assessing reliability in extreme scenarios, such as exploring what happens when we have long lock hold times due to network delays, and also experimenting with application workloads that are infeasible to run in production. While these might seem like pretty standard things you want to do in your system, this was not possible at Meta before TAOBench due to scale and other constraints. I'll talk about one example in particular on how we were able to help the rollout of new transactional use cases. So before TAOBench, when an application wanted to onboard to the transactional API that Aaron talked about, the process was they would test out, make sure the code worked, and it wasn't until very late in the development process that they could actually see if they would have a lot of contention errors. And if they did, then sometimes they had to sort of roll back months of work and start from scratch again. So it was very frustrating both for the system engineers as well as application developers due to these reoccurring delays because they couldn't test speculative workloads. The new process with TAOBench is that we first capture and replicate the workload that we want to roll out to production, and we measure these errors with TAOBench, replicating them in a testing environment so you're able to very quickly see early on in the development process if there will be issues with this particular workload you're trying to run. And as a result, so we actually tested this with the team, and we found some errors, and when they later rolled it out in production, they had the same errors, demonstrating that TAOBench is able to enable end-to-end testing early in the development process and speed up the rollout of new features and optimizations. Outside of Meta, TAOBench has also been applied to help a range of databases. So it's been integrated into TiDB's benchmarking suite, which is exciting, both to like verify new features as well as make sure there are no regressions. For Yugabyte, we actually helped them identify several performance bugs and opportunities. When we ran our benchmark initially on the system, we found the performance was unexpectedly slow, and working with them, we identified this was actually due to a Postgres monitoring bottleneck with exclusive locks. And in conclusion, there's also more details in the paper. So in conclusion, we are presenting a new benchmark, TAOBench, that accurately captures Meta's social network workloads, and it has a simple API that's easily extensible to other systems. And this benchmark has already had impact at both Meta and beyond. We hope that TAOBench can be useful for you. More info can be found at this website. I'm happy to take any questions. Thank you.
Yep. Thanks, Audrey. Thank you. Okay, cool. I do have a question online. So besides SQLDB, can TAOBench benchmark KV data stores with distributed deployments such as Redis, such as TiDB? Yeah.
Yes, definitely. So our API is actually closer to a key value store than a SQL API. So it can definitely be extended to those systems. It just, when we were writing the paper, we decided to focus on distributed SQL databases. Yeah, but if there's any interest in that, we're happy to work with you to build out that adapter layer.
Yep. Okay, cool. Yep. Thanks, Audrey. So is there any questions in the office, in the meeting room?
Another question online. It just shows up.
Okay. So I will read it out. So does or will TAOBench support range query test, like a list of associate reads?
Yep, that's a great question. So in our paper, we mentioned that as future work, and it is something that is in progress. So currently we do not have it, but we do plan to add that.
I have two questions.
Yeah.
First one is that you mentioned that the conflict is really like intentional. I'm just wondering how this is very specific to Meta, or this is a generic like applied or generic thing applied to different types of levels. So the intentional like conflicts.
Yeah, that's a good question. So unfortunately, there's not that much data available on other social networks, so we're not able to see. I think a lot of transactional benchmarks, the conflicts result from sort of races, data races. They're not, I wouldn't characterize them as intentional, but I think it was really interesting for us to see that basically applications were doing things they knew were bad. Like they would lead to these errors, but they knew they could ignore those errors.
Yeah.
And it's sort of interesting observation of how applications in some cases are like abusing the system because they know the system will provide stronger guarantees.
Sure. So from another angle, in case that we know those are like the social hazard for those workloads, what are some of your recommendations for the data students to handle those cases?
Yeah, that's a good question. So I think at Meta, at least what I've seen is try to limit the power you give to application developers, like limit as much as possible, because you'll find, especially at such large scale, so many different use cases, people will abuse the APIs in ways they were not designed for, and application developers are very creative in that sense. I think that's partially why TAO has chose to be very conservative in its rollout and also start with one-shot transactions, because it's, as you get more and more complex and you support more features, it also becomes a challenge of like balancing those needs with the majority, like 99-point-something% of requests that don't need those guarantees. So it's a fine line to walk, and I don't think there's one right answer, but general principles are to sort of really figure out what the application developer needs and find the simplest and safest way to provide that.
Cool. That is actually not my second question. My second question actually is, so you're benchmarking TAO's workload on all, basically all the majority of the new SQL databases.
Yeah.
What are some of the motivations to do this when you start this research?
Yeah, I think because our workload is like a serving workload with high contention and transactions, it's definitely a more challenging workload. So we felt by running them against like up and coming and somewhat established SQL databases, we could first generate interest in the benchmark, but also see how they compare against.
Okay. Cool. Thank you.
Okay, cool. Thanks, Audrey. Okay. Thanks a lot for the great presentation. Okay, so lastly, Yang will explain the reasons behind TiDB's performance in TAOBench. So Yang Zhang is a software engineer on TiKV storage team. Before that, he worked in Google as part of the Spanner team. Okay, cool. Hello, Yang. Yeah.
Hi, thank you for the introduction. I'm Yang, but you can also call me Andy. My topic today is to how we use TiDB to be a predictably performant database in social network and as well as other environments. So first, I want to say thank you to Audrey and people behind TAOBench to put TiDB on the radar. As you can see here, TiDB actually did a great job in the benchmark. So you can see that the latency increased a little bit while the throughput goes up, but that's within like a reasonable range. But please allow me to do another round of advertising for TiDB. So besides great performance, what TiDB also provides our user is simplicity. I call it like a one-stop infrastructure for modern applications. So here's an example. This is a website created by a bunch of PingCAP engineers in their spare time. So it's like a website built on top of GitHub public data. And basically, for example, if we search RocksDB here, it will show you some graphs. For example, like which country contributed to RocksDB the most. Like to build such a web application in the past, usually requires a lot of effort. You probably need a database dashboard transaction processing to be the source of truth. And in addition to that, you also probably need some ETL pipelines. You also need some analytical frameworks to do the application. Because as you can see here, at the top right corner, the dataset is pretty large. It's 5 billion rows of data. While with TiDB, it's pretty simple for you. One cluster is all you need, and you can run this like aggregation just using SQL. Another thing TiDB gives you is like a bunch of great toolings. For example, here this is a query plan. This is very helpful if you have some problems in your production and you want to debug it. Okay, so no more further ado. Let's get started with today's main topic. This is agenda. So first, I want to talk about like my understanding of benchmark. Then I'm going to talk about like several features or optimizations TiDB did that makes it a great product in social network scenario. And at the end, I'm going to talk about some other optimizations we did to make it good in other environments. So first, benchmark. So being good has different meanings in different contexts. For example, like a great car in drag racing doesn't mean it's a good car on a snowy day, right? I think the same principle applies to databases as well. I guess this is also the point Audrey was trying to make. Through the years, TiDB has been adopted by and trusted, verified by thousands of users globally. There are like financial firms, there are internet companies, gaming companies, and AI. Like obviously, different users in different industries have different expectations and requirements on the databases they use. So next, I'm going to talk about like why TiDB is a great product, in social network scenario, or some optimizations we did to make it good in such environments. First, let's do a quick recap of TiDB's architecture, or if you're not familiar with TiDB, let's do a brief introduction. So TiDB is like a layered architecture. At the top, we have a SQL layer called TiDB, and at the bottom, we have a storage layer called TiDB. And nowadays, we also have another type of storage layer. It's called Flash. That basically is a columnar storage, and it's aiming to solve OLTP workload. And on the side, we also have like a centralized control component. It's called system driver. So in TiDB, we split the data into shards, into Markov shards, and each shard has multiple replicas. Between replicas, we use rough algorithm to keep them consistent with each other. And as a child, we use populator transaction model to implement the distributed transaction, or we can say a cross-shard transaction. Like at a single node level, we use RocksDB to be the local storage engine.
Yeah, one question. So it seems that as you started, this has impacted your application developers. You shard your database.
I mean, this, yeah, that's what I'm going to talk in the following sections. Basically, what this architecture or sharding strategy gives you is like a linear scalability, right? So compared to other products that doesn't use this architecture, this gives you performance like as you add more and more servers. And so it seems TiDB do the sharding for you. It saves you a lot of effort. You don't need to like actively maintain the cluster.
And from the application perspective, there's no need to change the SQL in order to
right.
Right.
Yeah. So one social network nature mentioned by Audrey was traffic skew, or we can say hotspot. So that is a pretty common problem in distributed systems, and I mean probably all other systems. And it's bad because it causes like high latency or high, especially tail latency. So with the support of the architecture I just mentioned, TiDB allows TiDB can support low place speed. So for example, if you have a specific shard, it's receiving a lot more data, a lot more requests than others. What we did is we just need to split this specific shards into like smaller shards. And then we can evenly distribute the leader of this shard to different servers, so that then we can utilize all the servers' resources. And so now the hotspot issue is somehow or somewhat mitigated or resolved. So here's a graph showing you this process. As we can see, around 15 p.m. The workload started from code, and around like 3 minutes later, all 3 nodes have their CPU fully loaded, and the QPS reaches its limit. So with that being said, this process is actually very responsive, and it's a fast process. Another thing about our tooling, we provide a tool called hotspot visualizer or key visualizer, which allows you to monitor whether there's a hotspot in your system. So imagine if you have a hotspot in a specific area, you will notice like a very light point here, or at the X. If you have like a certain time, your system is receiving extremely large request, you will notice some light points over the time. So the second optimization I want to talk about is one dismiss. As mentioned earlier, co-location is another thing being observed in social network scenario. So TiDB's optimization for that is one dismiss. Because we're a distributed database, and we're a sort of like a transactional distributed database. Like transaction guarantee is what we provide to our users. I mean, traditionally, the transaction are implemented using two-phase commit, but we did like this so-called one-phase commit as an optimization. So when all the keys the transaction touches is within one shard, it can happen within just one round trip. So basically, we save the network time. Since we're already talking about one-phase commit, I want to mention another optimization we did. So it's not like designed for this scenario, but it's worth mentioning, which is about async commit. It's another optimization we did for basically what it did is, so instead of waiting for the coordinator to be committed, we just need we just return to the client after all the pre-writes are successful. This is still correct because the reason why we have to wait for the primary to be committed or the coordinator to be committed is that we have to have a way to tell what's the state of the transaction. But to answer that question, we doesn't need to. That's not the only way. We don't have to wait for the primary to be committed because one way to answer that question is whether all the pre-writes succeed or not. So the implementation is pretty straightforward. Instead of like in the past, we keep a pointer that points to primary from secondaries, and now we just create another bunch of pointers that points from primary to secondaries. So when crash happens, we just need to do a quick lookup to figure out whether that transaction succeeds or not. So this is a very general introduction of this structure, but if you're interested, we have like a blog on our website, so you can just search for that. So that's two optimizations I want to share with you that TiDB did for social network standards. Next, I'm going to share with you some like several other optimizations we did for other environments in real world cases. So first is throttling. So in TiDB or in TiDB, we have several many types of throttling. So basically, we can categorize those into two big parts. One is throttling the background jobs, because sometimes even the user have a very stable, steady traffic, it's still possible for the overall traffic to go beyond the resource limit, and that is that. Especially you're building a distributed systems, or you're building a system on cloud. So we have bunch of rate limiters to throttle those background activities. For example, convection, rate limiter, backup, analyze. Yeah. So here is a graph showing you that before, with and without this optimization, what the performance looks like. So with the on the left, you can see with the throttling, the performance is pretty stable or smooth, and on the right is pretty like bumpy. But besides throttling the background activities, we also do some foreground request throttling. The reason is that so we don't want to overflow the lower storage engine. In our case, the RockCB, because like RockCB has a mechanism or self-protection mechanism called rest stalls. That happens whenever the background activity cannot catch up with the foreground request. And it's that because when that happens, we will observe like a dramatic QPS drop and latency increase. So what we did was we created like a mechanism that observes underlying storage engine's status and push the pressure to the client. So just make the whole process a little bit friendly to the front end. And here's a graph showing you the kind of like the effects of this mechanism. As you can see, there's a plateau there. That means that's when this mechanism kicks in. Basically, it means that when there's a like backlog background activities, and it reaches some threshold, we just like slow down all the traffic so that the backlogs can be cleaned or at least maintained at a reasonable level. So another general optimization is saving the resource. This is very critical, especially we're now build TiDB Cloud. Believe it or not, like saving resource also means it's also like critical to performance. So yeah, here I kind of like bring up like a concept which is called bursting. So if you go beyond the resource, you will get up some penalties from the TAOBench. One way we save resource is through introducing a new storage engine called RuffEng. Because not sure if you, in the past we used RuxDB to store RuffLog, and as you may know, RuxDB is a LS tree structure, and it has a very big problem called amplification, because whenever you write a key into the system to the disk, you probably have to replay this writes multiple times, because you know, you may write into a smaller files first, and then you will merge into like a bigger file, and you will then merge with another bigger file to a even larger file. So, but you know, like RuffLog has certain natures. It's basically sequential write and delete. What that implies is that we don't really need the merge operation of RuxDB, or in other words, RuxDB is too heavy for us. So we created like an engine called RuffEngine. It's basically a log as data store. We just sort of manage a bunch of SS tables. So through this optimization, we were able to save a lot of I/O resource. As you can see here, depends on the environments. We were able to reduce the like total I/O usage to around 15% to 40%. Yeah. So that's all the optimizations I want to share with you guys. If you have any questions, I'm happy to answer them.
Okay, cool. Thank you very much, Andy. So yes, I do see two questions online. So well, the first one is not maybe for Andy's, maybe for TAOBench. So how TiDB can help to improve on the TAO benchmark? Well,
okay, sure. I'm not familiar with it, but I know some of the context of this. So TiDB is a graph API built on a package. So basically, they use a key value store, maybe similar to the GraphX on Spark. So it's serving graph queries like faster. That is basically TiDB. But I think for the knowledge, I mean, this may be a valid question for the people who build the TiDB. But I think definitely that is something maybe you can probably call it a graph database. I believe that your benchmark can also work on graph database.
Yeah, should be.
Okay. Well, yeah, more context. I think TiDB is maybe this hackathon project.
Yeah.
In our past hackathon.
Oh.
Yeah. Some people built a graph database based on TiDB. They named it TiDB.
So it's not an official feature.
It's not an official product from PingCAP, at least. Yeah. But we have a blog post. Maybe we can send it to the chat window, and yeah, you guys can learn more about it.
Yep. Okay, cool. Thank you. So the second question would be, so is there any specific motivation or performance advantage of using Raft for replication instead of Paxos-based protocol, such as the one used in Google Spanner, the one used in OceanBase? I think this is for Andy.
I would say it's not I mean, performance was not considered when we make the decision. It's more like a engineering choice. Rough is, I mean, I'm not sure if you read the paper or not, but rough is definitely more detailed and more clear and easier to implement it. That's why we choose rough over Paxos, ideally. Yeah, and I mean, rough is basically a multi-part Paxos implementation. So I don't think there's like a significant difference between rough and Paxos. And the second question is, when using similar modular graph, how do we compare TiDB with Yugabytes? Actually, I'm not quite sure about Yugabytes architecture. Are you familiar with it?
Let me try. I know some of them, but let me see. So, okay, let's see. So I know that you know that the TiDB architecture is like we have like a compute layer, we call it TiDB servers, and then we have storage layer. Actually, we have two storage engines. One is a column storage, the other is row store. The column storage is called TiDB, so we have layer architecture. And beyond that, we also have component called the placement driver, and we try to handle the failovers, handle scale up, scale down, and things like that. So that is basically TiDB architecture. And I think one interesting thing about that is that all the TiDBs implementation is from scratch. The TiDB servers are implemented in Go. We are not using any MySQL code base. And I think for Yugabyte, they also have layer architecture. They do have a storage layer. I forget the name, but it's called maybe distributed doc, something like that.
Yeah,
there's a document, and then they have like a basically they extend Postgres to talk to their storage layer. That is what they do. So one advantage of that is that basically you can see from Yugabyte website, they basically call all the Postgres features, right? But I think if you look at the databases, the most important thing is how the database behave under the real workload. And I think with that regard, TiDB is more mature compared with Yugabyte, because we have like more adoptions in different industries, and we have been tested like more extensively. So that is what I would say.
Yeah. In other words, I mean, probably it means like TiDB is sort of like a bottom up, and they are sort of top down.
Yeah.
Yeah.
Yep. Okay, cool. So the last question would be, does TiDB throttling mainly targeting on reads or writes?
Both. So yeah, both. To throttle the background activity that benefit both the read and write, while to throttle the foreground request is mostly writes. I think that's answer for the question.
Cool. I have a question, no more online. So when we were running TiDB, we saw they were like optimistic and pessimistic transactions. I was wondering if you could give a little context on why you decided to support two modes and what's like the breakdown of usage for each of them.
Yeah, maybe I can take this question. That's an interesting one. And actually, at the beginning, TiDB only supports optimistic transaction. At that time, most of the adoptions of TiDB are from like the digital native business or the internet companies. Yes, for their application, is they require performance and quite high throughput. So the optimistic transaction will be better for that. And after 1 or 2 years, because TiDB is proved by the production, and we got some financial use cases, and especially we have chance to do some evaluating for like core banking application, they have requirement for the proximity transaction. Yeah, so we add features to support that. Yeah, but I think it's not easy to switch from the two mode. So we support both. Yeah, I can maybe give another. I think your list answer I can probably give another perspective. So I think one key difference from the user's perspective, one key difference optimized transaction and maximized transaction is that. So for optimized transactions, the transactions can fail because of conflict. For maximized transactions, the transaction can only fail without the issue, but cannot fail with transactions. When the prereq is successful, the transaction has to be successful. That is the key difference. So if the user of transaction, they need to, from the application side, they need to have the retry of the transaction logic in the application to make the application actually work. Otherwise, there can be the case that the application basically the transaction fails, but the application needs to retry because of conflict. But for maximized transactions, once you reach certain point, it has to be successful. So for those applications, they don't need to have the retry logic. So that is because we start with the DMD, which are building applications, then we are okay working with them so that they can have the blocks in the application handle the transaction retry. But for the traditional, it's very hard for them to change the application and handle the behavior difference between TiDB and the optimized transaction in TiDB and the maximized transactions, the Oracle or other like systems. So that's why we build the maximized transactions.
I see. So the real difference between the two methods, if I'm understanding correctly, one of them has built-in retries.
No, not retries. Because maximized, you have logs, for example, right?
But the optimistic, you don't have logs at all.
No, so that's different. So they have logs, but they have logs in the commit stage, not in the prereq stage. For example, I can give you an example. In pessimistic transactions, when you try to write something, right, you first write log, and that log is persistent on the storage. Then the other transaction will see that, they will wait. Right. But for pessimistic, this one also has in memory, and then they will try to persistent that during the commit. And during that commit, they can see the conflict and one of them will fail. And that is the difference. So that's why they have additional failure cases compared with pessimistic.
So the guarantees you can have are the same.
Yeah.
But it's slightly different, or there's a retry.
And interestingly, these two modes are compatible. We can have one transaction pessimistic, the other ones because of the company.
Do you know the breakdown of like roughly X%?
Right now, I think our default mode is pessimistic because that is easier on the application side, right? Because you don't have to have the try the application. So that
very cool. Thank you.
So thank you very much, everyone. We have actually a small gifts for all of the speakers. It's a very nice photo.
Sure. So for ours, sorry you are not here, but we'll meet you somewhere probably later. And we have some slides. It's a T-shirt from PingCAP. It has like a MySQL statement. It's like something from TiDB. And we also have I don't know, bottle.
Oh, bottle.
That's a SQL knowledge. It's like a slide start from owner speakers. We're reading it, not American. And this is also a speaker exclusive, and we only give them to people who deliver tech talk in our Meetup conferences or things like that. So
I'm actually seeing Aaron next week.
Okay, sure.
So
I will see you. Okay.
Well, thank you very much. It's very much appreciated.
Okay, cool. So, last but not least, if you want to join our community, if you want to try TiDB Cloud, you can scan the relevant barcode on the screen. Okay, thank you very much for everyone to join us today, and I guess I will see you next time.